Electrons with a certain kinetic energy pass through a powdered crystalline sample and are incident on a fluorescent screen. The diagram shows a sketch of the diffraction pattern produced. A change is made, and the second pattern is produced. Which change could produce the second pattern? Okay, so we can see that when going from our first to second pattern, the concentric rings that we have here are getting further spaced apart. So what could achieve this? So when you have electrons passing through a crystalline sample, they will diffract. The crystalline sample acts like a diffraction grating. A crystalline sample is a sample which has a regular array of atoms, so the atoms are arranged in some kind of repeating pattern throughout the structure. A metal is an example of something which has a crystalline structure. So if I just draw a few atoms like this, so this acts as a diffraction grating. The electrons act as a wave. When they pass through the crystalline structure, they diffract, and then you will see regions of constructive and destructive interference where these waves interfere. So, how do we make the concentric rings further apart? We can do that in a few ways, in a couple of ways. One is we can change the size of the wavelength. So if we make our wavelength bigger relative to the gap size, we can increase the amount of diffraction that we have up until a point. Similarly, if we were to decrease the gap size, so make the spacing between the atoms smaller, that can also increase the amount of diffraction. So the underlying principle there is, if you increase the wavelength relative to the gap size, that can increase diffraction up until a point. And we can do that by either increasing the wavelength or decreasing the gap size. So that will increase the amount of diffraction we have, that will increase the spread of the waves, and that will spread the pattern out like we see over here. These concentric rings will get further spaced apart. Alright, so let's look at our options. So option A, decreasing the kinetic energy of the electrons. So if we decrease the kinetic energy, that will decrease the momentum of the electrons, as Ke is half mv squared. So decreasing the kinetic energy decreases the speed, which decreases the momentum. And if we decrease momentum, if we think about this equation here, lambda is equal to h over p, by decreasing momentum, we will increase the wavelength, which is what we want to have happen. We want to increase the wavelength. That will increase the amount of diffraction that we have, and therefore spread the pattern out like we see over here. So our answer would be A. Let's think about the other options as well. So option B, replacing the electrons with protons with the same kinetic energy. Okay, so the mass therefore increases. When going from electrons to protons, the mass increases by about a factor of 2,000. Same kinetic energy, so kinetic energy stays the same. So let's think about this equation for kinetic energy. Kinetic energy is p squared over 2m. So this is an alternative form for the kinetic energy equation that is useful. It's useful in this case because we can just directly relate the wavelength equation, de Broglie wavelength equation that we have over here, which depends on momentum, to this equation, which also depends on momentum. So they both share p in common, and therefore this form of the equation is useful when it comes to linking these two equations together. Okay, so I'll rearrange this for momentum. So p squared is equal to 2m. I'll just write the kinetic energy as E. So we're increasing the mass as we're going from electrons to protons. The kinetic energy stays the same. That means the momentum increases. And then if we think about lambda is equal to h over p, increasing the momentum will decrease the wavelength. We want to increase the wavelength to increase the amount of diffraction that we have. So it can't be B. Option C, using a crystalline sample with a wider spacing between its atoms. So as discussed before, we want the spacing to get smaller between the atoms to increase the amount of diffraction. Smaller gap spacing, larger wavelength, either of those two things or both of those things will increase the amount of diffraction that we have. So it can't be C. And then option D, moving the screen closer to the crystalline sample. Okay, so let's say that these are our waves. They're traveling towards our crystalline sample, which I'm representing as this line over here. They diffract and spread out, so our wave travels in different directions. I'm going to consider these to be the maximas. So what I mean by that is, if we placed a screen over, let's say here, these points would be regions of max constructive interference, or bright spots, on our diagram. If we move this screen closer to the sample, then what will happen is these maxima will get closer together. And if the maxima get closer together, well, that's not what's happening here. The maxima, the concentric rings, are getting further apart. So we'd actually want to move our screen away from the crystalline sample to achieve the desired effect. So it can't be D.